theory of valence shell electron pairs, and they're being repelled. So it's repulsion theory. We're looking at how the electrons, those negatively charged pairs of electrons, repel each other and therefore maximize their distance from each other around the outer shell of an atom. And as the electrons move to try and relieve that pressure, that repulsion, they take the chemically bonded atoms with them. So as we said yesterday, it's a bit like my hand and moving my arm. I move my arm, then my hand has no choice but to move with it. And likewise, with the atoms connected through chemical bonds, if the electrons repel each other and move away from each other, then the atoms move with them. So if we understand how the electrons repel each other and how they take up at the lowest energy possible state by maximizing bond angles, we'll understand the shape of the molecules. So the first example is carbon dioxide. It's a black pen instead of a red. CO2. And how many electrons for a carbon? 4. How many electrons? 6, yeah. So our electron total is going to be, so we'll produce this Lewis structure of carbon dioxide, CO2, of exactly 16 electrons. Remember, you must have an even number for your electron count, because the shells and the subshells are filled by even numbers of electrons. So if you had an odd number, it would be something odd about that. We'll choose for our central atom, we'll choose carbon for the central atom, because it needs the most electrons to complete its shell. And we can draw in the oxygen, just anywhere, doesn't have to be exact opposites. We get the ball rolling, a chemical bond between the two atoms. We want to use the remaining electrons to fill the octets of the outer atoms first. So we can draw lone pairs for the oxygens, using up 12 electrons, all of our electrons used up. But our picture isn't finished, because we haven't completed the octet for the carbon atom itself. So we'll borrow a pair of electrons from one oxygen to make a double bond, borrow another pair of electrons from the second oxygen atom to make a second double bond. Now our octets are complete. Now of course, some people, I'll redraw this quickly. Some people might have went with an example like this. Why not just use one of the two oxygens for a triple bond? In each case, we've got octets complete. So why is this picture nicer than this picture? So again, when you have multiple opportunities or multiple possibilities for your final structure, use formal charge to work out which one is best. Best structure should minimize formal charge. So, how many electrons should a carbon atom control? Should control 6. How many does it control in this picture? 6. So it is electrically neutral. How many should the carbon control? How many does it control? 4. One of the 2 electrons in each bond, 1, 2, 3, 4. And then the oxygen on the other side, same environment, so same formal charge, 0. So with 2 equally balanced oxygen to carbon double bonds, all 3 atoms are balanced and electrically neutral. However, if we look at the example below, what's the formal charge of this oxygen? Plus 1, as somebody says loud and proud. Okay? Controls 1, 2, 3, 4, 5 of the 8 electrons around it, 1 short from the 6 it's supposed to be. How about the carbon? Formal charge? 0, because it does control the force, so that's still fine. And then in the oxygen on the other end, we have -1. So we've got multiple charged atoms, and also nasty positive and negatives, which is difficult to really rationalize. So showing the formal charges can sometimes help you decide between one answer and another. Don't lose sight of the fact that the filling of octets, the completing of shells, is the most important thing when you build your Lewis structure. We just have two examples, we said, which break that octet rule. Two elements which we said were hypervalent, and they were Elvis thought he knew. No? What was the question? We've forgotten it already. What elements break the octet rule? Which elements are hypervalent? Phosphorus and sulfur, okay. Right. So there's the Lewis structure, our final answer. You've got to be able to hear your answer. So we're looking to see how these electron pairs repel each other and how that repulsion forces the electrons as far apart as possible. There's only so far they can escape from each other because they've got to stay in orbit, so to speak, around that particular atom they're bonded to. We've got 1, 2 chemical bonds. The two chemical bonds get as far away from each other as possible and move to opposite sides of the carbon, as we've shown. And therefore the shape that we see for the molecule is linear. Linear molecule with bond angles of, from the oxygen to carbon to oxygen, 180. So that's our final answer on carbon dioxide, CO2. So when we're building the structure, 5 steps again, we have 4 oxygens. Each of those oxygens brings 6 electrons to build the Lewis structure. And the sulfur as well, the low oxygen in the table, also needs 6 electrons, which gives us a count of 5 times 6, 30. And then we've also got the charge of the sulfate ion, which is -2, which gives us another 2 electrons. It gives us a total of 32. We choose sulfur as the central atom, even though its requirement for electrons to fill its shell is the same as oxygen, needing 2 electrons to look like either neon or argon. Sulfur is lower in the periodic table than oxygen. So it's a bigger atom, and bigger atoms should be capable of forming more chemical bonds, not greater initial surface area. So sulfur goes at the center, you connect the oxygens around it, you fill the octets of the oxygen atoms, and it leaves us with a picture with the sulfur having an octet of 8. So it looks like we might be okay at this point. So let's digress back to what that would look like. The initial picture we get for the sulfate ion with 4 individual chemical bonds, it looks as if we've done our job because octets are complete. Of course, we said with sulfur it's hypervalent and it can have 8 or 10 or 12 electrons in its outer shell. So which picture is the correct one? To work out which is the more correct picture, we can use formal charge. Oxygen should control 6 electrons in its outer shell. Each of the oxygens here controls 7. Yeah? So there's initially a formal charge on each of these oxygens of -1. Likewise, the sulfur atom in the center should control 6 electrons as well. From its octet, it only controls 1 in each bond, 4 of the 8. So the formal charge of the sulfur is Plus 2. Coming up too short. It should control 6, only controls 4. So it's a plus 2 charge. And that fits with our formal charge for the molecule, because we said the sulfate ion has a charge of -2. -1 4 times over, plus 2, it does come to that overall charge of -2. We've got a lot of charge here, like we saw in the phosphate before it. Every single atom has formal charge. And we have atoms with opposing positive and negative. That's really bad for stability. So, let's use a pair of electrons to make a double bond. So we have to imagine that these electrons are gone. And if we make another bond, a double bond between these two atoms, now there's oxygen again, these are gone. So the oxygen controls 1, 2, 3, 4, 5, 6 of the 8 electrons around it. So that -1 charge disappears in the oxygen. The sulfur, now with 10 electrons around it, but it's hypervalent, it's allowed. With 10 electrons and controlling 1, 2, 3, 4, 5, charge in the sulfur is now +1. So things are better. Less atoms with charge, and we've reduced the charge on the sulfur. But we can take it a step further, try that trick again. So we use this lone pair of electrons on the end there, and turn it into a double bond. Removes the charge from the oxygen, and it completely removes the charge from the sulfur. Using the hypervalent nature, making a second double bond to the oxygens, now only 2 of our atoms have formal charge. And we don't have that nasty positive to negative formal charge as well. So the 12 electrons around the sulfur actually gives us our best picture. And again, the individual charges add up to the sum of the island, sulfate -2. So this is the best picture we can draw for the sulfate. We've got a Lewis structure, our best Lewis structure, and it fits with the formal charges and reduces formal charge. What about shape? We've got 1, 2, 3, 4 chemical bonds around this central atom. 2 of them are double bonds, but we don't count double bonds twice, because it's just to double the electrons, but they're still packed in between those 2 atoms. That takes more energy, and the atoms have to be more imaginative in how they juggle those 4 electrons, because they can't fit into the same single space, but it's still 4 electrons just between the 2 atoms. You can't move the electrons, otherwise it doesn't become a bond between those 2 atoms. Remember, the bond is overlapping mutual space, so those 4 electrons have to occupy that mutual space. So double bonds and triple bonds we just treat like a single bond. With 4 chemical bonds around the central point, the shape of the molecule is tetrahedral. Tetrahedral with a bond angle of 109.4 degrees. So between this bond and this bond, an angle of 109.4, this bond and this bond, this bond and this bond, this bond and this bond around the back, 109. Every single angle, the molecule's symmetrical. All of the bonds and the atoms have got an equal distance between every other atom and every other chemical bond.